Happy Tuesday, everyone. I'm Lori DeToro, Communications Manager. Thank you for joining us today to learn more about axial flux motor benefits in our first Current and Wave webinar. We are pleased that you are here and also happy to have Matrishvan Raval, Head of Product for Turntide, with us. Thanks so much for joining us, Matrishvan.
Thank you.
Before we get started, we have some housekeeping tips to share. Want to let you know that this presentation is being recorded and will be available on demand on the Current and Wave website. We will have time after the formal presentation to answer any questions you have, so please use the Q&A section to ask your questions anytime during the webinar, and we will answer as many as we can before we have to end time. We will also have a brief 3-question survey at the end of the webinar. We ask that you please answer the survey so that we can help you in the future and help plan upcoming webinars. That's it for housekeeping. Matrishvan, take it away.
Thanks, Lori. Welcome, everyone. Thank you for joining the webinar. Today, I'm going to talk about axial flux motor technology, the benefits of the axial flux motor technology, and how we can scale the axial flux motor technology from being a niche application mainstay to being used in mass applications and high volume applications as well. So I'll give you a bit of introduction about Turntide, the company that I'm working for. We'll go into what the axial flux motors are, what the tech and the physics behind the axial flux motor is, and the benefits that provides us. We'll also look at various market sectors and how it is really suitable for those end market sectors, and then things that we can do in a technical and manufacturing sense to scale the use and scope of the axial flux technology. We are a one-stop shop powertrain integration and design and manufacturing company. We were formed in 2021. The transport division was formed in 2021 by bringing together the power electronics expertise from Sevcon, which has been around since the 1960s, the axial flux motor and cooling pump technology from Avid, and the battery technology from Turntide. So we've been operating since 2021 as a provider of electrification powertrain technologies across batteries, inverters, motors, and cooling products for a wide range of customers in various market sectors. Just in terms of the market sectors where axial flux motors are particularly useful, I'll start off with the off-highway vehicles. They tend to have a lot of implements. One of the trends that we've seen in the off-highway market sector is it's a low volume, high mix category. We tend to have implements and functions that have high mix and high variety, but the individual volumes of the SKUs of the product tend to be low in number. Another key characteristic of the off-highway vehicles is that they tend to be very space constrained. This is where the axial flux motor technology is a natural fit. Because of its compact form factor, because of the high torque density, it is easily integratable into off-highway vehicles and provide all the torque and power necessary for those. Another key market sector for us where we've seen a lot of demand is premium automotive. That's where they're requiring the highest torque delivery, the highest power delivery, and sometimes a high speed delivery as well, again in a very compact race car form factor. That is where, again, the compact axial length of the axial flux motor makes it super useful. Light passenger vehicles, the low voltage end of axial flux motors are very useful in light passenger vehicles. We've seen a lot of interest and application for 48 and 96 volt axial flux motors. Typically, the general consensus would be radial flux motors are good for 10, 20, 30 to about 50 and 100 kilowatt applications that are useful for light passenger vehicle. But with axial flux motors, you tend to get that extra boost of performance, which can differentiate your product. So we've seen a lot of customer inquiries where they're looking for that differentiation, and the axial flux technology is providing that to them. As far as commercial bus and truck markets go, The general view is that there's plenty of space to play with. That tends to be correct, but with e-axle applications and hybrid applications, there's again a high amount of space constraint. We've seen inquiries in a lot of hybrid conversions in the commercial bus and truck space where they want to maintain all the engine components, but also need enough space and performance for fitting in electrification components. And that's again where the compact axial length of the axial flux motor is very useful. Um, there's a lot of regulation in the marine space that's driving demand for off-board motors and marine electrification. The larger sizes of motors, the larger diameter axial flux motors, which have the high torque, low speed operation, are particularly attractive in the marine space as well. Rail electrification is another interesting area where these are huge, massive, multi-ton vehicles where the motors are required per compartment. And we've had larger multi-stack axial flux motors to be very popular in the rail sector as well. This is a busy slide in terms of motor classifications. I'm going to spend a good chunk of time on this particular slide. Motor classification can be done across various parameters. One of them is the type of force that's driving the motor, whether it's reactance or reluctance. Another category would be the type of magnet, whether it's a permanent magnet or some sort of non-permanent magnet material that's used. And the topology of the magnet itself also drive the classification of motors. The key differentiation from a customer point of view that we've observed is the efficiency. So in the earlier phases of electrification for smaller vehicles, DC motors were very popular. They still are, but they tend to give you at most 60 to 80% in efficiency. And if you are to bring electrification into the mainstream, the 80% mark is simply not enough in terms of being at cost parity and efficiency parity with other forms of transport. So we move into PMAC and induction machines. Induction machines face a similar problem. Even at the high end of the induction machine, we're trying to get about 85% efficiency at the most. So the answer tends to be usually PMSM motors, your permanent magnet synchronous motors that tend to give you the highest torque density as well as the highest efficiency in its performance. Again, there's various classification, whether they're being driven by reactance forces or reluctance forces. The type of motor that we're going to discuss today are permanent magnet three-phase synchronous motors. And that's where we will delve into the axial versus radial comparison as well. So we're going to start off with the poll. Laurie, would you like to kick off the poll?
Yes, let me launch this poll for you. So, you know what? I can't launch it because I can't find it in my list. So why don't you ask the question and we'll launch our next poll?
Sure. So just as a quick introduction to the axial flux motors, it was, if you can guess when the axial flux motors were created, whether it was the 17, 18, or the 1900s. Keep your answer, and then we'll move on. Shall I move on, Laurie?
Yes, please. Sorry about that, Matrician.
No worries. So the first axial flux motor was, in fact, the first motor that Michael Faraday invented in 1821. It was of an axial flux topology. The radial flux motor, as the simple motor as that was called back then, was developed by Thomas Davenport in 1834. So here we've got a later model of the Faraday axial flux motor, which looks a lot more like the pancake motor arrangement that we're used to seeing today. So let's get into what differentiates an axial flux motor from a radial flux motor. It's based on the orientation of the magnetic flux. So if the magnetic flux is in direction radial to the axis of rotation, that's when you have a radial flux motor. Or if it's parallel to the axis of rotation, then you have the axial flux motor. And that is driven by the way and direction and topology of how the magnets are arranged. So if you can see on the diagram here, the axial flux motors have magnets arranged in such a way that the flux is parallel to the axis of rotation. Now, this particular poll, do we have the poll ready for this, Laurie?
Yes, we do have this
Yep.
one ready.
So just
So
a survey to ask people if they've actually tested an axial flux motor in-house for any projects, whether POCs or in production projects.
yeah, so this poll has been launched. We'll give you about 20 or 30 seconds to answer. So please make sure you answer this for us so that we can help know what we might want to do for future webinars and future content on the website. So we're going to give everyone about 10 more seconds to answer. And so far, the no's are winning.
Okay.
There are a few yeses. Again, give you a few more seconds before we end the poll. We're going to end it now, gang. And so 6% said yes, and
Okay.
94% said no. So that's your answer,
Great.
Magician.
So that's my audience actually. So good to know. We have a large audience that's not used axial flux motors before. So this should be useful. Feel free to share your knowledge, insights, and questions as we go along. So let's get into the physics of it. As motor users, the thing that you're interested in is the delivery of torque and power. And one of the most significant determinants of this, and therefore the determinant of how efficient the motor is your magnetic field strength. Now, your magnetic field strength will be a lot higher if your flux path is shorter. And the field strength of the motor tends to increase with the diameter of the rotor that's containing the magnetic material, and it also reduces as the length of the flux path tends to increase. So the ratio that we tend to work with in terms of determining that is the D2L ratio, diameter to length. With axial flux motors, you tend to have larger diameters and shorter axial lengths, so the magnetic flux has to travel a lot shorter path. The intensity of the flux is a lot higher in those instances. And so if you want much higher torque delivery, much higher power delivery, and therefore a lot greater efficiency as well, you tend to find that the D2L ratio is favoring the axial flux motors much more so than the radial flux motors. Some equations this is probably the only technical slide or semi-technical slide that you'll have on the presentation. With the radial flux motors, the torque tends to vary as the square of your diameter, whereas with the axial flux motor, the torque tends to vary as the cube of the diameter. Now, as you increase the size, the torque density stays the same with radial flux machines, but because of the cubic nature of diameter variance in terms of axial flux motor, as you're increasing the size, counterintuitively, your torque density also tends to increase with axial flux machines. So people tend to think that bigger machines will be less torque dense. That's not quite the case with axial flux machines. Bigger machines tend to be even more torque dense than the smaller machines as far as axial flux topology goes. With radial flux machine, you tend to have fairly heavy weight and high inertia in terms of rotor, whereas with axial flux machine, on a torque to torque comparison basis, you'll have much lower inertia rotor that can deliver the same or higher amount of torque. So what tends to happen because of the cubic nature of torque variance with respect to axial flux motors, you tend to get 2 to 4 times more torque density compared to the standard radial flux motor. So if you tend to convert that in terms of weight and volume savings, you'll have about 50% weight and volume savings for your powertrain. Now that is huge. If you're a vehicle designer, if you're a powertrain designer, almost halving your weight and space can lead to a lot of benefits, including more components in your powertrain, as well as making the whole system more efficient. So poll question, Laurie.
Yes, we have
We would like
another.
to know if you or your teams have implemented axial flux motor in any current vehicles or equipment, or actually are a user of one such equipment.
We've launched the poll, and I feel like the answers may be similar to the last poll,
Pretty
but
much, yes.
we'll give you about 20 or 30 seconds to answer, and then we will go ahead and end it and share the results. And yes, 5% yes, 95% no, which is kind of what you probably
Very
thought.
similar to the previous question.
Yes,
Yes.
excellent.
Okay, good to know. Another poll question. For the 5% that did say yes, if you've implemented, or the 95% that said no, if you haven't implemented an axial flux motor before, what was the main reason that led you to not implementing axial flux motors? Was it the availability of the product itself, or the price point, or the suitability to the application, or you simply were not aware of the existence of axial flux motors
Yeah,
or
and
looked into it?
we have launched this poll, and yeah, you can actually select more than one answer. So feel free to do that, and we'll give everybody about 15 more seconds to answer. And we appreciate y'all taking part in these right at the beginning. It helps Matricia know his audience, which we were pretty sure we knew our audience, but you're helping us know you even more. So we're going to end this and share the results. Matricia and I'll read those out.
Hmm.
Availability, 18% said that. Price, 45%.
Okay.
Suitability, 45%. And have not researched was 45%.
Okay. Yeah, because it's
Yeah,
multiple answers. Yeah.
yeah.
So your
So,
top contenders tend to be your price and suitability.
yeah, I'll close this
Okay.
poll and you can move on.
Yeah. So that was that actually confirms the thesis that I've had in terms of popularity of these machines. Um, as far as suitability goes, there's very specific applications that can benefit from the compactness of the product. And another key factor that's been holding back the popularity of axial flux motors is that the price point at which these motors are available in the wider market today is not as attractive as some of their radial flux counterparts. So that's a thesis that we've been working on. That's a thesis that we've taken into account, and I'll be talking later on about things that we're doing to make sure that the motors are available at that right price point for the mass market. So going back to the system level benefits that you can have from axial flux motors, you got two features supporting it. First is the high torque and power density of the motors themselves. The other factor is it can allow you to reduce your gearing ratio as well. Now, the bigger the rotor size and diameter of the motor, you tend to find that uh, it's operating in a high torque, low speed operating region. With that, you can afford to have much lower gearing ratios, or in some cases, have direct drive and eliminate gearing altogether. So you can have for every 10% reduction in vehicle weight, which is achieved because of the high torque density, as well as by simplifying the gearing mechanism, you can have improvements in the vehicle range by 13.7%. So this low vehicle weight leads to higher vehicle range, and high vehicle range ultimately leads to a lot lower total cost of ownership. We worked with some customers to try and define this TCO model as well, and so yeah, we're more than keen to have use cases and to have studies where we can demonstrate this lower TCO for the axial flux motors. Another key benefit that I want to talk about is the absence of cogging torque. Now, cogging torque is a phenomenon that occurs in permanent magnet motors where as the rotor moves, if you ever moved the rotor by hand, um, you can feel the rotor moving in discrete steps rather than smoothly rotating fairly uniformly. And this is because the permanent magnets in the rotor and the stage teeth, they're interacting, and that is creating a pulsating torque. Now, if you want a fairly smooth operation, which granted most vehicle operations would require a smooth, non-jerky, and precise motion, then the cogging torque is a fairly big evil. Now, in order to mitigate the cogging torque, you can use various techniques. You can skew your rotors in such a way that the cogging torque produced is less. You can also adjust your stated tooth shape to make sure that the cogging torque is reduced or minimized, or you can implement fairly sophisticated sensorless control algorithm techniques where at those instances the current is varied so that the torque is lowered when it cogs. So one of the areas where we researched and sort of improved our products is that uh, is the NVH performance of the motors. If you have segmented teeth in your design of your stators, you tend to get a lot higher cogging torque, and that leads to poor NVH performance. So what we've done is we've designed it in such a way that there's no segmented armatures, there's no segmented teeth in the stators, and so there's little to no cogging torque, almost immeasurably low, and therefore a lot higher and better NVH performance. Let's get into the types of axial flux machines. People thought that axial flux machines are only of a single type, but we can have multiple sub-varieties of that as well. And that can be done through the structure, i.e. the topology of the motor itself, what sort of cores you're using, what kind of slotting you're using, whether the type of winding distribution as well, and whether what sort of permanent magnets are being used. So the type of axial flux motors that we've tended to focus on are the dual stator single rotor type or the Common type, using an iron core. And the other type of motor that's fairly popular is your single stator double rotor type or the Taurus type. Now, why did we go for the double stator single rotor feature? We wanted to minimize we wanted to maximize the D2L ratio and minimize the machine length as much as possible, and also provide design modularity where we can do multiple stacking. And the designs that we had available had the DSSR topology, the double stator single rotor topology, that lended itself really well to the multiple stacking options as well. So just to diagrammatically illustrate that, the figure on the left here with the two stators and the single rotor is the Common type that we've gone for. It's without any steel discs. It's leading to a lot shorter machine length. And in terms of the cooling, you can have very effective winding cooling through indirect cooling jackets, as shown in the figure here. In motor design, we've found the use of simulation to be fairly useful. We've simulated on all fronts, and that includes finite element analysis for structural integrity for vibration performance. We've done computational fluid dynamics as well to make sure that the coolant flow is optimized for the design and performance of the motor. And perhaps the most important simulation tends to be the electromagnetic simulation as well. So we've had in-house expertise where we used tools like Maxwell and others to make sure that the electromagnetic design and performance is optimized to its highest level. So just an overall view on the DSSR topology and construction. At the top, we have the high voltage connector housing. This is typically rated to be up to a kilovolt. So high voltage applications up to about 860 volt can be covered while accounting for the ripple and the overshoots as well. We are constantly adapting and improving the connector housing designs for various orientations and for various types of phase cabling or busbar arrangements that are required for integration into end applications. The heart of the motor, that's the composite rotor with embedded permanent magnets held into the spider cage structure. So if you can see the red spider cage structure, that's got the black permanent magnets embedded into them. And then they're banded together with a carbon fiber tape to make sure that it can hit the right velocities as required by the application while still holding the magnets in place. We got the dual stator arrangement on either side of the rotor and cooling jackets. So this is a fairly conventional cooling circuit with a water ethylene glycol cooling mixture. The shape and the arrangement of the cooling fins, the cooling channels, is something that we are constantly researching and optimizing to give us the highest cooling efficiency with the lowest pressure drop as much as possible. So if I'm to summarize what the value proposition of the axial flux motors is, the first and the most clear benefit is the high torque and power delivery in a fairly thin design. So if you want a high performance application or your application has space constraints, or you can use the space for some other differentiating feature for your vehicle, then axial flux motor tends to be your motor of choice. As I mentioned with the topology before, this is a design that can be stacked. So you can have multiple stacks of these motors to give you a wide range of torque and power, and we'll cover the numbers in a few slides' time. Efficiency as well, uh, owing to the thermal design, the electromagnetic design, and the mechanical design improvements that we have done, we are able to hit the highest efficiency classes. We are easily at the IE4 efficiency class mark, and we are trying to hit IE5 and beyond with the new research that we're doing as well. Um, Cooling tends to be often ignored, but the fact that these motors are cooled using commonly used water ethylene glycol mixture makes it very popular and makes it easily integratable with other cooling circuits as well that can be used for inverters or power electronics. So if you were to use axial flux motors for your future projects, given that there's a large audience that hasn't had the chance to use it, what would your top reason for doing that be? Would it be the power density and the torque density that this offers, the efficiency performance, if you'd like to stay ahead of the competition in terms of differentiating factor, if you're fairly space constrained, or some other reason? So, Laurie, can we launch the poll?
We have launched it, and we will give you guys and gals a few seconds to answer. Right now, it looks like high torque and space constraint is winning out.
Mhm.
No one wants to stay ahead of the competition right now.
No.
No one. Um, but we did say the main reason. That may be a sub reason. So
Mhm.
give you about 10 more seconds for those who have not answered, and then we will share the results with you. All right, we are going to end and share. So maximum power density was 32%. Sorry, 23%. I read that backwards.
Mhm.
The number one was high torque requirement in a space constrained environment, 62%.
Yeah.
Maximum performance was 15%, and then staying ahead of the competition and other were 0%. So
Okay.
the three main ones were the three main ones.
I can guess the makeup of the audience from the answers itself. It's a very engineering heavy audience,
That's
maybe because they
fantastic.
selected the answer that we all thought as the
Well,
driving
we
piece. So
invited all the engineers to join us, and some of them
yeah,
decided to join us. So, yeah, we're ready to move on.
great. Thank you. So just to look at the portfolio, I'll explain the nomenclature in this diagram. We've got in the portfolio that we have, we've got continuous torques ranging from 100 to 1,000 Newton meters, and power ranging from 60 to about 400 kilowatts, and that's the rated continuous electrical power. So there's four main diameter classes that we've developed. We've developed the 25 centimeter, 30, 40, and 43 centimeter diameter classes. The one that's at the start of the numbers is referring to the number of stacks. So the first four motors that you see on the diagram, the 125, 130, 140, and 143, are single stack motors. And if you take two of the AF130s together, you get a double stack motor, the AF230. And that's what I mean when I refer to the modularity and stacking arrangement of the motors. You can have, we've tried and tested up to four stacks with these motors. So depending on your torque requirements, depending on your power requirements, we can mix and match and create the right stack product for the market. Yeah, just in terms of the numbers again, another salient point to notice here as you're going up in your diameter class, you're tending to go down in terms of the maximum operational speed of the motor. So this is thousands of RPMs. So we tend to go down from 12,000 RPM for our smaller diameter motors to about 3,700 RPM for our largest diameter motor, which is the AF143. If any of the numbers jump out, yeah. So the thing that jumps out to most people in this is how little weight is required to deliver these high amounts of torque and power, and the length is the axial length. So it's a fairly impressive axial length figure as well when you compare it with radial motors, which tend to be about 2 to 4 times in length for a similar diameter class. This is my favorite slide, which is where I get to talk about the improvements that we are making on various fronts. So if I get the poll results right, for most people, the price point and the availability has been a sore factor where why axial flux motors haven't been considered. One key way in which that can be addressed is by tooling up these designs. So if you do the right design for manufacture of the housing of the metal components and you're optimizing it fully, then these can be tooled up for high volume production as well, and that will significantly reduce your cost. That will bring it almost at parity or a slight premium with radial flux motors, and that's what we tend to do with the projects that we are working on right now. We're also considering using semi-automated or fully automated machine winding so that um, it can allow you to ramp up from tens of thousands to hundreds of thousands of motors in terms of annual production as well. Most of these motors tend to be limited by their thermal performance. So optimizing the thermal part, the cooling channel, is a key differentiator and can give you lots of benefit by allowing you to push the motors to work at even higher temperatures and lower flow rates. So a key research area for our thermofluids guys has been to optimize the design of the cooling channel by reducing the metallic length of the cooling channels as well, and by reducing the pressure drop that's experienced by the fluid that's flowing through the cooling channels. Um, a key ask in terms of warranty from customers tends to be in terms of hundreds of thousands of kilometers or multiple years. We've seen customers asking from what used to be a standard 4-year warranty up to now 8 or 10-year warranties for e-machines as well, and that's to bring it at parity with internal combustion engine performance, where engines tend to have that level of lifetime as well, and because these motors are the new engines, so to speak, for the electrification world, they are following a similar trend in terms of durability and reliability ask as well. So we've done a lot of research to try and improve the machine durability, the machine reliability, by which we can offer much higher lifetime and warranties. A key area there tends to be around bearing life, because they tend to be some of the first components that wear and tear out and reduce to and lead to a failure of the machine. That is something where we've invested a lot of time and research to try and improve and optimize the bearing design and select the right components so that you can get high lifetime as well. I had briefly touched about the simulations that we're doing. Just to expand on the electromagnetic side of things, it includes also selecting the right material and the right torque speed curve grade that we want from the magnetic material, as well as improving the slot pole geometry to get the most out of the design. Some of the applications where we've implemented these optimizations and performance benefits from there, as I said earlier, for premium automotive, it's used mainly for traction purposes for high performance e-motorbikes and automotive cars as well. There's a wide variety of applications in the commercial trucks and bus space, traction being the most common one, but we've had a lot of inquiries for electric power takeoff as well. Um, for larger trucks and buses, they can also be used for ancillary applications. So if you've got a huge, big 60-ton truck, then you'll need a fairly big cooling fan for cooling the battery electric vehicle circuit or the hybrid circuit as well. And the smaller diameter class of motors that we have, the 125 and the 130, are fairly popular for use for those ancillary applications as well. If you're also in the hydrogen game, I don't know how many hydrogen people have joined today, but we've got a solution for the hydrogen guys as well, because the smaller diameter, higher speed motors are also suitable for use as fuel cell superchargers. On the off-highway machinery, um, similar domain with a lot of variety of applications. You've got construction and mining equipment. You've got excavators, wheel loaders, and that's where you can use for traction, both track and others, and ancillary functions for slew and swing. Another interesting application for us was street sweepers. Now, they have so many implements and are so space constrained that the axial flux motor becomes very applicable for using street sweepers as well. So we've used these for traction as well as for sweeping implements on the street sweepers. There are many more exploratory areas for us as electrification grows in these areas. We've found multiple uses for the axial flux motors for generation as well. Just because they have the high torque and power delivery, they are equally efficient when it comes to power generation. So if you're not just using it for motoring purposes, you're using it for actual power generation purposes as well, and you want to get the maximum from mini generators, then these tend to be very popular for use in mobile generators, which are your water and wave power generators, or even small mobile wind power generators that are being developed. Aerospace and eVTOL is an area where your perhaps your biggest driving factor is your gravimetric power density. You want to minimize your aircraft weight and your powertrain weight as much as possible. And so if you're able to provide a fairly high gravimetric torque and power density, then these motors are golden as far as eVTOL applications are concerned. For marine sector, as I said before, regulation is driving a lot of it. For use on off-board motors, for marine propellers. We can also use it for auxiliary power on various hybrid boats, and for more industrial uses as winches and cranes on ships, and trains as well. Whether it's a light commercial railway or trams, these are used as traction implements on those. So, I'd like to conclude here by saying that the axial flux motors, they're inherently superior technology because they're able to offer you a lot higher performance that can allow you to have much smaller, lighter, higher efficiency, and more powerful vehicles at the end of the day. And we are, leading the way in terms of our core technology research and manufacturing methods to enable multiple markets to reap the benefits of these and make axial flux motors as popular as possible and for use in mass applications as much as possible. So, with that, I would like to thank you all for patiently listening to me, and we shall take questions now.
Yes, we do have questions, and remember, we've got a little time, so please send in your questions if you haven't asked yet. And the first one we have is, if axial flux motors have been around for hundreds of years, why are radial flux far more popular, and what
Mhm.
stops uh, axial flux from being successful?
Great question. So they have been around for hundreds of years, but what was productionized the most, the type of technology that has had the most productionization investment in it, is the radial flux technology. Um, if your application is not length constrained in any way, then you tend to go for a radial flux topology as an easy fix. And because it's had the most amount of investment in terms of productionization, typically 200 years of investment in productionization, they are at a price point where they're readily available and cheap. What we're trying to do is take the axial flux motors through a similar journey. They've simply not had the attention or investment as radial flux motors have had. Um, so even though if it's an inherently better technology, if we get it to the same point in terms of its productionization investment journey, then our thesis is that it will take off in an even bigger way and capture a lot of the radial flux motor market as well.
Excellent. And you may want to stop sharing your screen.
That's a good idea. Let me stop sharing.
We had a lot of us all over the place there. Um, so I'm going to look and see if we have another question that has come in. We've not. Why is power density important, and what is a good power density or a strong power density for an axial flux motor?
So when people are looking at motors, they tend to focus on torque density as a first point of call. But if your speed profile is very important, your torque speed profile overall is what makes the power density important as well. So if you are for example, developing a supercar application, it's not just the torque delivery, but the speed at which a given torque is delivered that makes the whole combination possible. That makes it suitable for that high speed application. So, depending on the specific torque speed profile that you require for your application, power density is the composite of the torque and speed multiplication, which is what makes power density a fairly important factor as well.
Excellent. So the next question is there a possibility of a non-magnet axial flux motor?
Mm-hmm. Interesting question. The what if you so the way I see this developing in the future is the arrangement itself of the magnets is what's giving you the higher torque density. If you go for non-magnetic material, you'll cancel out that benefit in terms of the torque density. So you'll you'll be at an even space. So the loss in torque density and power density that you're getting in radial flux motors by use of non-magnetic material can be evened out if you have the same uh, non-magnetic material in an axial flux topology. So if I were to compare non-magnetic material in a radial versus non-magnetic material in an axial flux motor, you'll still get higher torque and power density. So you're evening out the loss because of the use of non-magnetic material. But it's a very interesting concept and some food for thought as well.
So it seems primary applications, next question, by the way, it seems primary applications of axial flux motors are supercars, trucks, etc. Is it likely to disrupt the passenger car space?
Yes. So um, the trend that I have seen in passenger car electrification is that people are wanting to get higher and higher performance at a lower price point. So if I'm able to give an axial flux solution, which is, let's say, 2 to 3 times more torque and power dense at a price point which is just 1.2 or 1.5 times the radial flux solution, the market, the OEMs, the market itself will eventually move to a solution which is having a higher performance to cost efficiency, and that's what axial flux motor is providing. So I don't see that just as um, a premium market play. It is at the moment because of its current pricing, but with the new pricing that we're trying to target, we can disrupt the passenger market as well.
So the next question is explain if and turntide motors can how configurable turntide motors can be to meet customer specific torque requirements.
Mhm. So as I had explained in the stackability slide, we can go all the way from 100 to 1,000 newton meters in continuous torque just by changing either the diameter class or the stacking option. And because there are so many SKUs that are possible, um, we can fit we can fit the right torque speed profile curve with the right motor just because of the diameter class variation and the stacking variations. That's one point of customization. The other point of customization is the operating point with the highest efficiency. So you typically on a motor efficiency map, you've got a contour of efficiency islands, and we can optimize the turn count within the motor to make sure that the highest efficiency point island is meeting your desired operating point. So that's another technical point of customization as well. And the third point of customization is the physical integration into your powertrain. So be it the orientation of the cooling ports, the orientation of your connector box, the shaft and spline details as well. We have a wide variety of options where we can meet those cooling, mechanical, and other integration demands to suit your overall powertrain. So 3 points of customization: stacking modularity, turn counts for making sure the operating point is at the efficiency sweet spot, and then mechanical integration as well. You're on mute, Lori.
I am unmuting. So if radial flux motors, an increase in rotational speed typically improves the motor's efficiency. Is
Mhm.
rotational speed a factor for axial flux motor efficiency? And what are the limitations that need to be overcome?
So where I've seen the axial flux motor typically flourish is in the lower RPM range compared to the radial flux motors, and that's down to the mechanical arrangement. We can We can design and produce high, tens of thousands of RPM axial flux motors as well, but that's not its natural range of operation. As far as speed dependency of efficiency is concerned, yes, it follows the same logic and equation as radial flux motors in terms of speed of operation, improving and enhancing the efficiency because of the electromagnetic features that it has. So yeah, my answer would be yes, it's the same as the radial flux motor as far as speed efficiency goes, and but the sweet spot is the lower speed operation.
Well, the questions keep coming, so let me ask you the next one.
We're good to
How
go.
good is the possibility of axial flux motors for power steering control?
Power steering control. The low voltage axial flux motors are suitable for it. Um, you'll have a much lighter footprint, and so with power steering, one of the biggest asks we have is the ease with which the driver can do the power steering, and therefore this lighter weight, even with low voltage axial flux motors, can help with that selling point, with that differentiation. So definitely a good use case for the, let's say, a 48 volt low voltage axial flux motor.
Okay, well, that was our last question. So I want to say that I appreciate everyone joining us. Um, and also want to ask you to answer the survey at the end. Don't forget to do that. Matrishvan, thank you so much for being here with us to give us this great information. You're such a wealth of knowledge and expert on this, and we really appreciate it. To our attendees, please stay to answer the survey and also go to Current and Wave to register for our January webinar, which will talk about the market for and what the market is doing for electric and hybrid configured vehicles and equipment. And that'll be toward the end of January. So thanks again, and we hope everyone has a great day. Thanks, Patricia.
Thank you all. Thank you, everyone. Cheers.